Hello. This will be a demonstration of Proposition 34 from Book 9 of Euclid's Elements, which says that if a number be neither one of those continually doubled from the dyad, or in other words, if this number is not a power of 2, nor is its half odd, it is both even times even and even times odd. That is to say, you can get this number both by multiplying an even number by an even number, and by multiplying an even number by an odd number. All we're given is the number a under such conditions as have been said before. That is, that it is not a power of 2, it is not one of those numbers which you get by continually doubling from the dyad, nor is half of a odd, or in other words, half of it is even. And what we want to prove is that the number a is both even times even and even times odd. For because the half of a is not odd and is therefore even, it is obviously even times even, because you can multiply the number 2 by its even half to get the number a, so that a is even times even. Next, we want to prove that the number a is even times odd. And the way Euclid goes about this is a little strange, but hopefully you'll understand it by the end of this. For if the number a is not even times odd, then it will be even times even only, because it's obviously not odd times odd, because it has a half, so it's obviously an even number. So if the number a, in other words, is only even times even, then if we continually have the number a, or as Euclid says, bisect it, as if it were a line, if we continually have the number a, we're eventually going to strike upon the dyad. For if this doesn't happen, then a will be even times odd. But here we're taking it as the fact that a is even times even only. So if we have it, then have it again, then have it again, then have it again, we'll eventually just reach the number 2, we'll reach the dyad. And because this is the case, that we get to the number 2 by this process of continual halving, we can therefore go backwards to get the number a by starting at the dyad and continually doubling, so that a is a power of 2. It is one of those numbers which you get by continually doubling from the dyad. But this is contrary to our given, which says that a is not such a number. And so, if the number a is not even times odd, or in other words, is even times even only, then the number a will both be a power of 2 and not be a power of 2, which is obviously impossible, and so we can conclude that the number a is even times odd as well. And this is what we set out to prove, that the number a is both even times even, which we had done in our first step, and even times odd, which we have done in our last step. So having done that, we are therefore done with the proposition, therefore, etc., Q, E, D. I do want to spend a little bit more time on this proposition, taking a number such as he's talking about. The number 12 would be such a number. For it is not a power of 2. You don't get the number 12 by starting at 1, then going to 2, then 4, then 8, then 16. You just don't get 12 that way. We also know that half of 12 is even, for half of it is 6. So what this proposition is going to tell us is that it is both even times even and even times odd. That it's even times even is pretty obvious. It's just 2 times 6. Because its half is even, the number 2, or the dyad multiplied by its half, will get you the number 12. So it is even times even. But what about it being even times odd? Well, if we have a particular example that's easy enough to verify, this is 4 times 3. You can get 12 by taking the even number 4 and multiplying it by the odd number 3. But how Euclid gets to this in the general case where we don't have a specific number is something like this. Imagine the powers of 2. Just imagine any power of 2. Say we start at 16. And we were to continually have it. Well, we would get to 8. We would then get to 4. We would then get to 2. Because 16 is one of those numbers you get by continually doubling 2. 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So 16 is one of those numbers, as I've been calling a power of 2. But the problem that you run into with, say, a number like 12 is that because we know it's not a power of 2, we're not going to hit the dyad. we're not going to hit the number 2, because if we did hit the number 2, that would imply we could start at the number 2 and continually double to get the number 12, which means that it would be a power of 2, which we know isn't the case, because we can do with 12, if we do this process of continually halving, we would get to 6, and then we would eventually hit not 2, but 3, and we can't go any further than 3 because it's an odd number. And so that's what the last step here is talking about. It's talking about this process of continually halving. And what it implies is if you eventually get to 2, then your original number was a power of 2. But if your original number is not a power of 2, then you'll never get the dyad, or you'll never get to 2 by doing this continual halving. So that's how we get to our given number being even times odd. Because if it is even times even only, it's a power of 2. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 935.